Bismillahirrahmanirrahim. How are you, students? Today we will study physics, lecture number 48, subject physics. Today's topic is entropy. But before going into detail of entropy, first we will explain thermodynamics. Let's revise the previous lecture. It's the study of the effects of work, heat, and energy on a system. Thermodynamics is only concerned with large-scale observation. Thermal equilibrium. When two different bodies are at the same temperature, then the bodies are said to be in thermal equilibrium. Two systems are in thermal equilibrium if and only if there is no net flow of heat between them when they are brought into thermal contact. A system temperature is an indicator of thermal equilibrium, because if two different systems are at same temperature, then the body is said to be in thermal equilibrium. Zeroth law of thermodynamics states that if two systems are separately found to be in thermal equilibrium with a third one, the first two systems are in thermal equilibrium with each other. For temperature determines the direction of flow of thermal energy between two bodies in thermal equilibrium. Temperature is also a measure of the average kinetic energy of the particles in a substance. Change in state of a system are produced by the interaction with the environment through heat and work. Heat is invisible, weightless, and can flow from one body into another body. Work is the heat energy which is converted into mechanical energy. Heat is the random motion of the particles in the gas that is degraded from the kinetic energy. And heat is identified as it comes across system boundaries. The amount of heat needed to go from one state to another state is path dependent. Heat and work are two different ways of transferring energy from one system to another. The distinction between heat and work is important in the field of thermodynamics. Heat is the transfer of thermal energy. Heat is the transfer of thermal energy between the system, while work is the transfer of mechanical energy between the two systems. Work is transfer of mechanical energy. Heat is the transfer of thermal energy. Transfer of thermal energy. System. Anything which are kept in consideration is called system. Everything external to the system is known as surrounding. The thermodynamic system and the surroundings are separated by an envelope called boundary of a system. Thermodynamics, universe. When system plus surrounding combines, it gives you universe. This have definite boundaries, so it is called a system. And the atmosphere, everything external to the system is called surrounding. This is boundary, and together they make a universe. Internal energy is defined as the energy associated with the random disorder motion of molecules. Now, first law of thermodynamics. First law of thermodynamics states that heat given to a system is used to increase the internal energy of the system, plus some amount of heat is used to do work against the system. If the process is isothermal, then the temperature of the system remains constant. Temperature of the system Pressure of the system remains constant. Isothermal process. Adiabatic process. An adiabatic process occurs without transferring heat or mass between a thermodynamic system and its surrounding, in which no heat enter or leave the system. Such process is called adiabatic process. Second law of thermodynamics. Second law of thermodynamics states that the total entropy of an isolated system can never decrease over time and is constant if and only if processes are reversible. Isothermal means isolated systems spontaneously evolve towards thermodynamic equilibrium, the state with maximum entropy. Second law of thermodynamics have two statements. One is Celsius statement and the other one is Kelvin statement. Kelvin statement. And Celsius statement. Kelvin statement. First we will study Kelvin statement. Heat cannot flow itself from cool body to a hotter body. It's Celsius statement. Heat cannot flow from cool body to hot body. Body to hot body without the expenditure of energy. Heat, it can be stated as like this. Heat can be made to flow from cool body to hot body by the expenditure of energy. Refrigerator transfer heat from cool body to hot body. Inside the temperature is low, the room temperature which is surrounding is high. So it take heat from the inside and give it to the surrounding by the expenditure of energy. If you didn't provide the electricity, didn't provide the energy, heat cannot be made to flow from cool body to hot body. So Celsius statement is heat can be made to flow from cool body to hot body by the expenditure of energy. Entropy is the measure of disorder in a system. All system gains entropy over time. Celsius Kelvin statement. It is impossible for a system to undergo a cyclic process whose sole effect are the flow of heat into the system from a cooled reservoir and to flow from an equal amount of heat out of the system into a hot reservoir. It means that no heat engine continuously operates in a cyclic process. No heat engine continuously operate in a cyclic process. No heat engine can operate continuously in a cyclic process. Now, Carnot engine. Carnot engine consists of 4 steps: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. From A to B, temperature of the system remains constant. So T1, temperature T1 will remain T2. Adiabatically, no heat enter or leave the system. No heat enter or leave the system. Isothermally, again compression, the temperature remains constant. And adiabatically, no heat enter or leave the system. So Carnot engine consists of 4 steps: isothermal expansion and isothermal compression, adiabatic expansion and adiabatic compression. When the system undergoes from A to B isothermal, the temperature of the system remains constant. So pressure and volume changes. Pressure and volume changes during this process. Now, when it goes from B to C, no heat enter or leave the system. So temperature will decrease from T1 to T2. Work is done at the cost of the internal energy of the system. Work is done at the cost of the internal energy of the system. If there is decrease in the internal energy of the system, the temperature of the system falls. Now, when the system undergoes from C to D isothermal compression, the temperature of the system drops and the temperature of the system remains constant and pressure and volume changes. There will be, so the process is compression, so pressure and volume increases. Now adiabatic compression. No heat enter or leave the system and the system is allowed to compress. So pressure and volume increase, volume and temperature increases. So the system returns to its original state, PVT. It starts from pressure, volume and temperature and the system returns to the same state after passing through isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression. So a process in which undergoes two isothermal process and two adiabatic process is called CARNOT engine. So CARNOT engine is an engine which operates continuously in a cyclic process. Or CARNOT engine can be stated as like this. No heat engine can be more efficient than CARNOT engine operating between the same two temperature reservoir. One is LTR, low temperature reservoir, and HTR, high temperature reservoir. So this process is isothermal expansion. Temperature remains constant. It's adiabatic compression, so no heat enter or leave the system. Isothermal compression, temperature remains constant. No heat enter or leave the system. Now, efficiency of Carnot engine is written as efficiency is the ratio of work done divided by input. Work done is equal to Q1 minus Q2. So, work done is equal to Q1 minus Q2 divided by Q1 is equal to Q1 divided by Q1 minus Q2 divided by Q1 is equal to 1 minus Q2 divided by Q1 multiplied by 100%. This is percentage efficiency. In terms of temperature, it is written as percentage efficiency is equal to now entropy. Entropy is the measure of a system thermal energy per unit temperature that is available for doing useful work. Because work is obtained from order molecular motion, the amount of entropy is also a measure of the molecular disorder or randomness of a system. Or entropy can be defined as disorderness of a system. The disorderness of a system. Disorderness of a system is called entropy. If you take temperature from a system or you give temperature to the system, you disturb the natural order of the system. You increase the disorderness of a system, so entropy of the system increase. Now, entropy. Why life always seems to get more complicated? Morphy law states anything that go wrong will go wrong. Anything will go wrong, will go wrong. Anything that goes wrong will go wrong. The pithy statement references the annoying tendency of life to cause trouble and make things difficult. Problems seems to arise naturally on their own, while solutions always requires our attention, energy, and efforts. Life never seems to just work itself out for us. If anything, our lives becomes more complicated and gradually decline into disorder rather than remaining simple and structured. Now, there is a tendency in nature to proceed in a direction that increases the randomness of a system. A random system is one that lacks a regular arrangement of its parts. This tendency towards randomness is called entropy. Entropy is a measure of disorderness of a molecule. Disorderness of a molecule. Entropy is represented by S and can be defined in a simple qualitative ways as a measure of the degree of randomness of the particles, such as molecules in a system. Entropy has the dimension of energy divided by temperature, which has a unit joule per Kelvin. Unit of entropy is joule per Kelvin in the international system of units. Entropy is equal to del S is equal to del Q divided by del T, or S is equal to del Q divided by T, joule per Kelvin. Joule per Kelvin is the unit, and entropy is symbolically represented by S. A campfire is an example of entropy. The solid wood burns and becomes ashes. Smokes and gas are all of which spread energy outward more easily than the solid fuel. Ice melting, salt or sugar dissolving, making popcorn, and boiling water for tea are processed with increased entropy in your kitchen. So, whenever there is change in temperature, entropy of the system increases. Entropy is represented by del S, and it is equal to Q divided by T. This applies only to the reversible path, even if the system actually follows an irreversible path. To calculate the entropy for an irreversible process, model it as a reversible process. When energy is absorbed, Q is positive and entropy increases. When energy is expelled, Q is negative and entropy decreases. When heat is taken from a system, entropy decreases. When heat is given to a system, entropy of the system increases. If the particle represents gas molecules at normal temperature inside a closed container, which of the illustrated configurations came first? This will came first, and this will after, because entropy of the system always increases. This came first and this came after. Disorderness is more probably than order. Now, entropy. This is with high entropy, more kinetic energy. Entropy decreases. Entropy more decreases, and entropy more decreases. So we go from disorderedness to orderness. So entropy of the system decreases, which is not possible practically. Which is more disorder, the glass of ice chips or the glass of water? This is more, the disorderedness is more in this or in this. This is your home assignment. Here, highly order. Orderness decreases, which causes increase in entropy, more disorder. In gases, entropy disorderness is more. liquid disorderness is less as compared to gas. Here disorderness is more less. So here entropy is greater, here in liquid entropy is less, and solid is more less. Now entropy criteria in different process. Spontaneous process, entropy will be always greater than 0. In equilibrium process, entropy is equal to 0. And impossible process, entropy will be always less than 0. So spontaneous process, entropy of the system is always greater than 0. In equilibrium process, the entropy is equal to 0. And impossible process, entropy is less than 0. So here in enthalpy, the difference between enthalpy is denoted by H, the measure of total heat contents in a thermodynamic system under constant pressure. If you measure the total heat contents under constant pressure, it is called enthalpy, and entropy is represented by S, and it is the measure of the level of disorderness in a thermodynamic system. So shortly we can say that entropy is the measure of disorderness of a system, or the unavailability of useful energy, the unavailability of energy for useful work done. So the disorderness, molecular disorderness of a system is called entropy. If you mix hot water with cool water, you cannot separate the molecules which have more energy than the molecules which have less energy. So you increase the entropy. So this is called entropy is the measure of disorderness of a system. Thank you, students. Allah Hafiz. Wish you best of luck.